Dr. Chris Eliasmith is the co-CEO of Applied Brain Research. Chris is a professor at the University of Waterloo, appointed in the Philosophy and Systems Design Engineering departments, and cross-appointed to the Computer Science department. He holds the Canada Research Chair in Theoretical Neuroscience and is the director of the Center for Theoretical Neuroscience, CTN, at the University of Waterloo. Chris has published over 100 articles and 2 books, including Neural Engineering and How to Build a Brain. And in 2013, he gave a fascinating talk about at TEDx Waterloo about the insightful process of presenting a work about building a brain. In 2015, Chris won the prestigious NSERC Polanyi Award for his research, and I'm looking forward to his talk on the brain, a lesson in computing. Enjoy it.
Hi. My name is Chris Eliasmith. I'm co-CEO of Applied Brain Research and a professor at the University of Waterloo. What I want to talk to you about today is what we can come to understand from looking at how the brain computes. The first thing we might want to ask is, what does the brain compute? And this, in fact, is something we're all very familiar with, but sometimes it's interesting to take a close look from a really directly computational perspective. Some of the things that brains can do much better than our standard computers is compute extremely complicated dynamics. This is an example of table tennis. You can see this ball is moving incredibly fast. It has spin on it. There's all kinds of nonlinear dynamics going on, not only in terms of just the movement of the ball, but airflow, and the body itself has all kinds of nonlinear dynamics. Nevertheless, the brain is tracking, making strategic decisions about where to place the ball next, and executing all the motor commands required to hit a ball which is moving in very strange ways. This is what amazes us about the brain. And this, of course, is just one thing it does. It's also amazingly good at processing language and understanding complex thoughts, having conversations, playing chess, driving cars, you name it. So these are the kinds of computations that we would like to get out of our machines as well. And the dynamics of the brain aren't just evident from looking at its behavior, but it's clearly the way it's put together all the way down. What I'm showing here is a group of neurons that are receiving an input, and they are responding to that input as a population. And it's interesting if you just take a look at a single neuron, what you can see is that a lot of these inputs leading to it, these are called dendrites, are lighting up without anything happening in the main cell itself. But after a while, if there's enough activity in these dendrites leading into the cell itself is active, generates this very brief pulse of voltage, which we can see with this in this movie here. And that then sends information to other neurons in the population, which are doing similar kinds of processing. So there's this continuous, real-time, online processing, which is highly dynamic. It has sort of no obvious discretization, except perhaps when we see the single neuron spike. It either spikes or it doesn't. It's not partially active. But not only are these groups of dynamics, also unsurprisingly, individual neurons are dynamic as well. So in this case, we can look at what happens when we put in a constant input. So at the top, we can see the input to the cell. And at the bottom, we can see what the output of a single cell looks like in terms of its voltage. And one thing you'll notice is that it's extremely nonlinear in several different ways. One is that it starts to activate only after a certain amount of input is given to it. So it's sort of nonlinear in state. It's also nonlinear over time in the sense that it gets a constant input, but its response itself is slowing down. So you can see that over time, the amount of responsiveness to the same input can change. So we have these 2 kinds of nonlinearity. We have nonlinearity in state, which you can also see by these extremely rapid brief pulses. And we have nonlinearity in time in the fact that the response changes over time, even with a constant input. So the brain is clearly dynamic at many different levels of description. And if we're interested in computing the same kinds of functions that brains compute, maybe we want something about that sort of dynamics to be incorporated into the hardware that we're building as well. Now, why might this matter? And this might be obvious to many of you, but really it comes down to efficiency. What we can do with a certain amount of power. One of the most amazing things about the brain is that it does all of those things I described before, playing tennis, playing chess, having conversations, with 20 watts of power. Now, in my lab at the University of Waterloo, we've actually built the world's largest functional brain model. It's called SPAWN. And what we once did a calculation where we said, well, okay, if we take the model SPAWN and scale it up, it's much smaller than an actual brain. But if we scale it all the way up to the size of a full brain, how many watts would it take to run that same model on a GPU? And the answer is over a gigawatt. So clearly the compute that we're using, right, is somehow very different in the way that it is implementing what we think are analogous kinds of computations. So our model spikes, it has different kinds of neurotransmitters, it's solving decision-making, perception, and action problems. But nevertheless, it's doing it with much less efficiency. Now, of course, the reason we think this is because the hardware of the brain is very finely tuned to the algorithms that the brain is trying to execute. So this massive difference in efficiency, of course, is one that we see in the context of doing the kinds of things that brains do. If we tried to get human brains to render video extremely efficiently, they would probably be much less efficient than our GPUs. So this kind of brings us to the first lesson I think we can glean from looking at the brain. And in fact, this is a lesson we can glean from just looking at compute in general, is that probably our hardware needs to match the kinds of algorithms that we want to run on it. So the algorithms, in some sense, determine the right sorts of hardware decisions that we're making when building the hardware. What does this mean to match algorithms? I think we can understand this in a couple of different ways. One is starting at the highest level, so thinking more like about the behaviors that we want the system as a whole to implement. So this isn't a new idea. You know, Kolmogorov had pointed out long ago that we can have many different systems, all of which are Turing machines, but they can have extremely different efficiencies for solving particular kinds of problems. So often translating from one architecture to another architecture, the cost of that translation is much greater than the cost of the compute itself. So this isn't a new idea, but it's an important one. And I think it's one where when we start thinking about brain algorithms, we begin to notice that the kinds of algorithms brains are natural at implementing, or that, you know, that they exhibit, are much different than the kinds of compute that we often get out of our standard computers. So the sorts of algorithms that we might want to focus on when we're looking at brain types of computation are dynamic ones, for all the reasons that I gave at the beginning. If we look at standard neural network methods, we have some neural networks that are used for dynamics in the sense that they're used for time series. So if you have a time series problem, you often turn to an LSTM, or you might turn to a transformer in the case of something like language, or even video processing and so on now. But these, in fact, are not dynamical systems. They actually come out of a history more in computer science, where you get one computation happening, and then you have a discrete step to another computation, and then a discrete step to another computation. So they're not fundamentally continuous dynamical systems. They're discrete systems, and we essentially ignore the transitions that happen between those steps. Brains aren't like that at all. They're continuous dynamical systems, which have very different theoretical properties and practical properties than discontinuous or discrete dynamical systems. Taking this into account, we recently suggested a new kind of neural network, which turns out to be, in fact, an optimal dynamical system for compressing temporal information. So it's based on a continuous dynamical system formulation, and it gives us something called an LMU, or Legendre memory unit, which turns out to actually do a lot better than LSTMs and transformers on many different time series problems. This is something I'm not going to dive into in this particular talk, but there is a talk I'm giving tomorrow where I will dive into that and talk a lot more about what optimal means, how it performs at different tasks, and so on. But in any case, the real point here is that, you know, we want to find at a high level, at the algorithmic level, the kinds of computations that are similar to the sorts that the brain seems to be doing. And in this case, I would argue that the LMU is doing something much more like a brain than things like LSTMs, transformers, or other kinds of computational paradigms that people have proposed in the past. So we want to find algorithm types that are going to match the sorts of behaviors that we want to get out of our system. And those are going to have consequences for the kind of hardware we're going to want to build. This is also true at the much lower level of looking at the individual computational components. So here I'm thinking not in terms of the high-level algorithm, but rather in terms of what do each of the basic compute elements do when we're running different sorts of neural networks in this particular instance. So what I've got in this movie is a simulation that we built with some software called Mango that we have also released. And it's showing a difference between processing through a spiking neural network and a non-spiking neural network. And so in this case, the processing is extremely simple. We're just having a constant input here in terms of a sine wave. We're sending that same signal through the top where we've got a bunch of spiking neurons. what you can see those spiking neurons are doing is generating exactly that kind of nonlinearity that we saw in the real neuron. So it's either on or off, and the sort of time at which that input signal is provided to it determines the time at which it turns on or off. In the case of a non-spiking neuron at the bottom, we have a nonlinearity in the sense that, it's not responding for a lot of the input signal, but then it does respond at every single instant in time, right? And so we see this sort of turning on, and then it responds, and then it turns off. Now, if you look at, in this case, the computation that we're doing is essentially just sending the information from one group of neurons to the next. In the context of a spiking signal, that those spikes arrive at the dendrites, as we saw in that movie, and they actually get turned into, so they sort of get spread over time, turned into a little temporal response in the dendrites. And if enough of those happen close enough together, you can actually sort of see a reproduction of the original input signal. So again, this begins to look kind of like the original input. Again, it's not responding to the lower half of the sine wave, but only to the upper half of the sine wave. And it's definitely quite noisy. You see a lot of variation around the actual correct answer, but nevertheless, the information is getting through in some way. At the bottom, we see the same kind of thing, that same exact response is, in fact, transmitted from one population of neurons to the next. And there's sort of, in some ways, not a lot of difference between what is sent and what is received. Now, why this particular type of computation might be interesting to look at from a hardware perspective, I'll get to in a moment. But before I get there, I think it's in some ways really easy to sort of grasp the core difference between a spiking neural network and a non-spiking neural network by looking at one equation. And that's the equation which describes the response of the neuron. In the case of a non-spiking network, the activity A of the neuron is equal to some nonlinear function of its input x, right? So you can think of x as the state and A as the output. And we can see that this is a very clear and, in fact, fairly simple relation, and it has nothing to do with time. So at any particular moment, it doesn't matter if it's in the past or the future, if a state is given to that neuron, it will have a particular output. This is very different from spiking neurons. So in a spiking neuron, we have an activity, and it's a function of the state, of course. We want it to be sensitive to its input, but it's also a function of time. And so the dynamics in a spiking neural network are built into the basic compute element, that is the single neuron. So if anyone ever asks you, oh, what's the difference between spiking and non-spiking neurons? Here is a clear difference, right? That the fundamental compute element in one case is sensitive to the state, and in the other case, it's sensitive to the state and time. Another way of saying that is that the dynamics are built in to the compute elements in a more direct manner. All right, so why do those kinds of computational differences matter? There's several reasons. So one is that really what you can think of that we're doing here is essentially sparsifying information over time. It's been well known for ages that if we have a weight matrix and it's extremely dense, that requires a lot of computation. And if we can sparsify that weight matrix and preserve the function, then that'll be good from a hardware perspective because we'll have to do fewer multiplies and accumulates. The same is true over time. We're sending far less information. In fact, we can just send one bit at each moment in time. And only at those times where the neuron actually spikes. And this is very different from a rate neuron, which is sending an 8-bit or 32-bit number at every moment in time. In the simulation above, we're sending, we're running the simulation at 1 millisecond time step. And so in the top, we're sending about 50 bits. And in the bottom, we're sending about, if it was 8 bits, 50 times, or 1,000 times 8, right? So 8,000 8 kilobits. So very different amounts of communication. There's also a lot less computation happening in the receiving population in the spiking network compared to the non-spiking network. So every time a spike arrives, we have to do a memory lookup, or every time a new value from our input arrives, we have to do a memory lookup to say, well, how do I weight this? And in the case of the spiking neurons, we only have 50 of those lookups to do. And in the case of the continuous rate neuron, we're going to have to be doing, 1,000 of them, right? If we have a continuous 1 second signal over sampled at 1 sample per millisecond. So again, a lot fewer memory lookups, meaning a lot less computation, and last but not least, we're also doing much cheaper computation. So in the case of the spiking neurons, you get a spike, you look up the weight, and now what do you do? Well, you multiply that weight times the activity. The activity is always 1 or 0, and it's always going to be 1 because we looked the weight up, meaning that all we have to do is accumulate the sum of all the weights that we looked up to give us the response to a bunch of input neurons for an output neuron. And so essentially, you're just doing adds. And in the case of the rate neuron, you look up all of the weights, and then you multiply those by the current activity level, which again is going to be an 8-bit number. So you have to do a multiply. You have to do a multiply for every one of the elements you look up, and then you sum them all together. So again, way less computation in case of a spiking neural network. All right. So one of the interesting things that happens if we begin to match our, low-level sort of computational elements to the sorts of techniques that we see used by the brain, we see a very significant potential increase in efficiency. All right. But of course, what I'm looking at is just one example of a particular aspect of biological computation that seems quite interesting, and that's looking at its dynamics. But there are many other aspects of biological computation that I haven't really touched on, which are probably important as well. Right? So the first one, biological computation tends to be dynamic. Our engineered computation tends to be step-based. Relatedly, our biological computation doesn't have any kind of clocking. Those steps in the engineered case are controlled by a clock. So in the biological case, that unclocked computation, sometimes called event-based computation, can save you a lot of problems trying to get a clock signal throughout a large system, for instance, or having to support very high clock speeds. In biological computation, almost everything that goes on there is analog. Of course, in the engineered case, most of what we're used to working with in our computational systems is digital. There are some really interesting trade-offs when we start, forcing all of the transistors to be digital versus their sort of natural analog states. And there's all kinds of interesting work that's gone on in trying to exploit analog computation, mostly for efficiency reasons. Biological computation tends to be slow. Neurons spike at most a kilohertz, which you almost never see. It's usually much, much lower, down to 1 to 10 hertz. Of course, in the computational domain, for our engineered computation, it's usually megahertz or gigahertz, much, much faster. The efficiency that we see for synaptic operations is less than a femtojoule, whereas we have much less efficient sort of picojoule levels, so about at least 3 orders of magnitude less efficient when we're looking at things like multiplies and accumulates. And in general, our biological computation is highly parallel, so everything kind of just flows through the system all at once, whereas in engineered computation, there's definitely been a movement towards more parallel computation, but it tends to be less parallel than what you see in biology. So these are many different ways that we can see differences between the sorts of engineering assumptions, if you will, that nature has made, and those that we have made in building our own designed computational systems. So the real challenge here is, well, which of all of these possible things matter, right? And how do they matter? And can I take them into account in my design, or can I not? Which ones are easy? Which ones are hard to include in hardware? Can we have unclocked digital implementations? How can we mix and match these, and so on? And this is an extremely difficult question, which I'm not going to be able to get to into gory detail. I've given a fair amount of detail in this idea of looking at dynamic versus sort of step-based approaches, all the way from the algorithmic right down to the hardware level. But let me take a quick look at one exploration into trying to understand which of these different ways that we can understand biological versus engineered computation might matter. So a few years ago, a group of us, so this was a collaboration between Stanford, my group at Waterloo, so Kwabena Boahen's group at Stanford, my group at Waterloo, and Rajit Manohar's group at Yale. We built a hardware prototype in which we tried to essentially use as many of those sorts of biological inspired computational methods as we could in a piece of prototype hardware. And that hardware is called BrainDrop. I'm happy to send you a paper on it if you'd like. And you can see that in there, we essentially picked all of the above. So what happens if we build a piece of hardware which is dynamic? So we have algorithms at the high level, and we have low level single neurons, all of which have their dynamics in the way that I kind of described previously. The system is purely event-based, so there's no clocking. The system's also like an analog digital hybrid, but all the compute is essentially done in analog. So we have dendrites and neurons, which are implemented in analog hardware, and then the spikes themselves are passed around sort of through digital fabric, but that's just the communication. It tends to be kind of slow. It has fairly slow clock speeds and so on. it turned out to be extremely efficient. So we did get synaptic operations on the order of 300 femtojoules, which is extremely good for hardware. Not at the level of the brain, of course, but still a significant improvement over digital neuromorphic chips, for instance. And it was also extremely parallel, as we tend to see in the brain. Now, why does it matter that we tried to put all of this stuff into one chip? Like, what were we going for? And you won't be surprised to hear that it's efficiency, right? So, inspired by what I talked about before, where we know the human brain is running at 20 watts, but we know that a brain scale model running on GPUs is a gigawatt, right? How much better can we do? And this, of course, is something that's inspired a lot of neuromorphic engineers over the years. So here's several examples. So in 2010, there was a very large neuromorphic computer, purely digital, based on sort of ARM architectures, where we calculated it would take about 24 megawatts to be running a brain scale model. More recently, Loihi from Intel has been released, and Spinnaker 2 is coming out. These are both sort of in a similar ballpark of about 2 megawatts. And Braindrop, if we scaled it up to the size of a human brain, we found to be about 38 kilowatts. So, very significant improvement. Again, still 3 orders of magnitude away from what a brain can do, but nevertheless, something which could be significant from an engineering perspective. But, right, so I'm not talking to a bunch of academics. Of course, we were all academics when we were building this project. But of course, you're not academics. And as a co-CEO of an AI company, I'm also not an academic. And it's important to look at some of the challenges that come along with these sorts of let me call it pure neuromorphic designs, right? We're trying to really adopt all of the biological approaches to computation that we can. One of the big challenges is that every single chip is different. So process variation is one of those things that digital design gets you away from. But in the world of analog, if you have a transistor that's slightly larger than another, it's going to have different sorts of computational properties, and you have to take those into account when you're designing algorithms to run. So every chip being different means that every chip needs its own program, a slightly different set of parameters to perform the same function across 2 different chips. So we have a set of optimizations that we developed, of course, which allows us to program these chips and get them to do things, but you have to do that optimization for each chip independently. You can think of this as kind of the same way that each brain has to learn how to perform its functions on its own. We can't download sort of predetermined, I'm a world-class tennis player from one brain to another. You can't copy programs. Another very intuitive way of thinking about this challenge. Now, why does this matter? Well, because that makes it not commercially deployable. If I can't build a chip and then replicate it a million times and have it do the same thing by just downloading the same software all over the place, that's essentially a non-starter from a commercial perspective. So in some ways, this brings us to our second lesson, which isn't really one that we're getting directly from biological computation, but it's one that I think is important from the perspective of trying to build AI commercially valuable hardware. And that is that not all the constraints going into designing our chips are going to be computational ones, right? Even if we could take all of the approaches that nature uses for designing chips, would that be a good idea? It's not clear the answer to that is yes. In fact, I think right now that the answer is no. So where does this leave us, right? How do we answer that question that we had before, that, what matters of those sort of biological approaches when coming to design my hardware? And in fact, we just have to consider everything in detail. So we can look at the dynamics, but then we want to ask the question, well, what level do we want to worry about? The algorithmic level and match that? Or do we want to worry about all the way down to the individual components, the neuron level? How about clocking? Should we not clock anything, or could we sort of clock some parts and not other parts? Same with analog. Analog is extremely efficient for certain operations. Can we just use analog in some places, where we can essentially encapsulate that variability I was talking about and not use it in other places, or have a digital to analog interface where the analog compute stays hidden? Should it be slow? Should it be fast? Should we have different clock regimes for different parts of the chip? This is especially relevant when we're thinking about combining analog and digital hybrid. Of course, as soon as we start doing things like that, the complexity of the engineering problem goes way up. So that can make life a lot more difficult from a commercial perspective. Will it be efficient or not? I think this generally is something that comes out of those other choices. How good of a job did we do of matching our hardware to the algorithms we want to run? That will help determine how efficient the chip is, right? Whether or not we can sort of successfully include analog components will also help determine how efficient our design is, and so on. And what this really leaves us with is an absolutely enormous design space, which in some ways is fantastic because there's going to be lots of exciting different ideas to try, ways of putting together, clocked and analog designs into digital design. There's just a million things to try. Of course, that's also a bit of a curse. So trying to find the right one in there can be extremely challenging. And from a commercial perspective, we'd like to just know what the best answer is and go with it. So, of course, in some ways, this is no answer to the problem of, well, what exactly do I include or what don't I include? That being said, at ABR, we are building a sort of brain-inspired chip. And we've decided to make certain kinds of compromises for exactly the reasons that I've described. And I'm going to, as I mentioned, talk about this chip a lot more tomorrow. But just to quickly go over it, we think that it is important if we want to compute brain-like operations, we want to do natural language processing, speech processing, be able to do all kinds of essentially real-time data processing, then picking algorithms that are essentially brain-inspired is going to be a critical thing to do. And down the road, I think it's also going to be critical to push that matching of dynamics right down to the neuron level. Will it be unclocked or clocked? This is going to depend on when or where we actually match the low-level dynamics. Once we're using spiking neurons, it doesn't make a lot of sense to keep a clock going. It's more intrinsically event-based computing when we're using spikes, and so it would make sense to sort of remove as much clocking as possible from certain parts of the design. We are going with something purely digital because we want to be able to program it, put the same software on, make sure it's very replicable, not worry about doing different optimizations for every chip. We do use fast clocks from the perspective of biology, but try to keep it as slow as possible from the perspective of standard engineering. And as many of you know, the slower you can keep your clock, the more efficient your design will be. And coupling all of these things together, for the applications we're targeting, we think that we will have something which is extremely efficient. And what this does for us overall is basically let us build what are currently cloud-sized neural network models and run them at the edge, run them in the tens of milliwatts, while being able to do things that people are doing now with BERT, like large-scale language models. And we think this is very attainable, and we also think that subsequent generations where we can adopt, in fact, more of those sort of biological approaches to computation are going to push the envelope even farther and make even larger models executable in very small power envelopes. So that being said, I hope it's clear that there were two main lessons I wanted to communicate. One is that you want to make sure that you're matching your hardware to your algorithms. And in the case of brain-like computation, so solving control problems, video processing, natural language, any sort of real-time application, that thinking about dynamical systems is going to be critical for doing that. Lesson number two is that while it would be wonderful to sort of adopt all the different approaches that the nature has taken to solving computational problems in our hardware, we probably don't want to do that. Not all of the constraints on building the best AI hardware are going to be computational, if you will, or efficiency-focused constraints. So in short, there really are advantages to building brain-inspired hardware. That inspiration can come at different levels, at the level of algorithms or at the level of how we sort of structure the actual compute in the hardware. But we have to compromise typically between practical concerns, so commercial concerns, and engineering concerns that are trying to achieve maximal efficiency. Thank you very much for your time and attention, and I look forward to your questions.
G'day, I'm joined with Chris live here for our Q&A session. And Chris, so lots of interesting stuff from you about the brain and what we can learn from it. What are the key things that you've learned in your journey in terms of looking at what the brain does and how it does it?
I'm sorry. Oh, what are the key things? I thought you said one of the key things. Right. Yeah, I think the most salient one is the one that I'm really trying to emphasize in this talk, which is that dynamics matter. You can't get away from time. And again, I like to point out that the main difference between artificial neural networks, as most people think about them, and networks in the brain is that the fundamental compute unit in an artificial neural network is not a function of time. The fundamental compute unit in a brain is a function of time, and it's just inescapable, right? So it's this essentially natural dynamics that we have as biological systems interacting with our environment, which is becoming more and more important for the kinds of engineered systems we're interested in building.
Yeah, so we had a question from Alexander online who asked, he's very interested in the unified analog approach on different components that you mentioned, and he's asking where you could read more about that.
Yeah, actually, so to be clear, the challenge with the analog approach isn't really a sort of theoretical one, and there's lots of places. So Kwabena Bohan, who we were working with in that project, has worked a lot on analog design, and in some ways, the challenges aren't so much with like how to design an analog circuit or how to use one. It comes to fabrication, right? And so when you fabricate the device, one of the things that digital approaches do for you is that they make you be able to treat every transistor identically. Unfortunately, fabrication has a lot of variation in it, and so you need to model that variation when you're at the analog level, because that variation now affects what the compute that a particular transistor is doing. Right. So if it's slightly larger, it might have a little more resistance. If it's slightly smaller, and those are the kinds of differences which are ones that you need to take into account when you actually program the device.
And it's something that analog, people who make analog chips for a living struggle with every day. And it's how to get a consistent yield, and then how to make sure that the transistor at one side of the die matches the characteristics of the transistor at the other side of the die. That's something that analog has long been difficult at, whereas people, as you say, in the digital realm, who only deal with the transistor as fully on or fully off, can tolerate yield variations or even characteristic changes across the die without any concern. And so that means that they're faster to execute at getting on the latest node, whereas analog, you spend much more time characterizing the process and the design and the response and alignment and tuning and all the rest of it. Yeah, it's a very salient point. Okay, so I have some interesting questions I got from this. I thought it was very cool, and you're emphasizing the concept of time in computing. It's something that we don't spend much time thinking about or talking about, but as programmer, early in my career, we were trained to write this, then this, and this, and this. It's very much a von Neumann way of coding. But what we're doing and what you're talking about in Neuromorphic is completely rethinking the way that things happen based on biology. As you say, it's more of a event-based computing model. What are the ways you think event-based computing might shine or prove itself as the more efficient solution? What are some key examples and ways that it might prove itself?
Yeah, well, I think when you're comparing different kinds of processors, essentially there's one metric which rules them all, and that's energy efficiency. And I think that's basically what a lot of people have really been focused on as the advantage of event-based computing, is that you're not sending information when you don't need to, and you're still being able to accomplish the tasks of interest. Now, the specific applications we tend to see this shine in are things like object tracking, right? Or cases where extremely rapid real-time-ish responses, which are faster than what you might get from standard cameras and so on, are needed, right? And so I think these are actually sort of different in some ways. So you can get big efficiency gains even when you're kind of computing slow information like language or natural speech or what have you. And you can also start doing things that you just couldn't otherwise do when you actually crank up the dynamics a lot and you put it into extremely high speed responses. So this can be things like flying drones very rapidly through a forest, right? Or trying to avoid a pedestrian stepping in front of a vehicle or something like that. So yeah, I think all of these kinds of dynamics can show up and be important in different ways. Sometimes it gives you additional function, and other times it just lets you save a lot of energy and perform the same function.
Okay, so perhaps in terms of autonomous driving, one example might be time for collision avoidance and reducing it down. In the example you gave of pedestrian, then perhaps the benchmark that showed might be the time to respond versus the speed of the car. Would that be a reasonable scenario?
Yeah, absolutely. Right. And I think you're raising an excellent point here, which is that we need our benchmarks to be time sensitive, right? So if you look around at all the AI benchmarks that are typically out there, one of the reasons people don't worry about time is because benchmarks generally don't care about time, right? How fast you do stuff. They do a little bit implicitly in that they're measuring watts, which is joules per second, right? So there's some notion of time in there in some of the metrics people care about. But yeah, I think you're right that we need to be expanding the set of benchmarks in order to cover these additional cases where dynamics are absolutely critical to the function itself.
Okay, well, we're out of time already, but thank you very much, Dr. Eliasmith, for joining us from Canada, our first keynote for this morning. And already you've stirred the pot with some interesting points there. We need more benchmarks that are sensitive to operations per second per watt.
Yep,
Thank you.
my pleasure. Thanks, David. Take care.
Bye.